Hey there, welcome to another video. So in this video, we're going to talk about the sum to product or product to sum formulas. I'm going to prove them for you. They're not that bad. We'll deal with a few examples. It'll be a briefer, I suppose, relatively briefer video, but I'm going to make sure that you understand how to do this. We'll end with a couple identities, how to prove them using these formulas. That way it really sinks in, and then solve an equation. So hope you're ready for it. So what we deal with the product to sum and sum to product formulas is how to really change between these products or these sine and cosine functions multiplied together and change them into a sum, or from a sum into a product. They're both very useful. They're both necessary later on in some math. So let's get right into it. First thing I'm going to do is prove the product into sum formulas for you. So let's take a look at let's see. This was the sum and difference formulas for sine and cosine. And here's what we're going to do. The whole idea behind these proofs is if you can add these together, what's going to happen is part of this equation is going to cancel. If you subtract them, on this one at least, another part's going to cancel, and we'll be able to solve for a product that we can write as a new identity. So let's go ahead and do that. Let's see what happens when we take these two formulas and we add them together. If we do add them, we're going to end up getting cosine of alpha minus beta plus cosine of alpha plus beta. So I'm adding these equations together. This would give us this. Equal to, the same thing happens here. We're adding these together. So if you remember anything about like systems of equations, you can add equations as long as you add one side and add the other side at the same time. So we're adding the left side, we're adding the right side, but what happens on the right-hand side? If we take a look at this, we would get cosine alpha, cosine beta, cosine alpha, cosine beta. We would get 2 cosine alpha, cosine beta. But what happens here? This is sine alpha sine beta minus sine alpha sine beta. Those are going to cancel. Those completely drop out of that equation. So when we're adding systems, add one side, add the other side, but those things cancel when we add. Now, if we solve for cosine alpha, cosine beta, we're going to get our first product into a sum formula. Let's just divide everything by 2. Now we're going to write this as a 1/2 in front instead of creating this fraction, because oftentimes we deal with fractions in here. Well, sometimes we deal with fractions in here, and it's just kind of awkward to do. So if we divide both sides by 2 or multiply both sides by 1/2, we end with cosine alpha, cosine beta, a product of cosine of one angle times cosine of a different angle. That's what's important here. Equals 1/2. Remember, we're dividing both sides by 2. Cosine alpha minus beta plus cosine alpha plus beta. So this takes, here's what it does. Takes cosine of one angle times cosine of another angle, a product, and changes it into a sum of cosines. Sometimes that's a lot easier to deal with. Sometimes it makes other things possible later on in math as well. Now, this is our first formula. What do we do about sine alpha times sine beta? Maybe there's a way to change that product into a sum. So if we take a look at our formulas that we've already dealt with, what if we didn't add? What if we just subtracted this entire system? Well, if we just subtracted them, we'd get cosine alpha minus beta minus cosine alpha plus beta. But on the right-hand side, remember that when we subtract more than one term, we've got to really think about subtracting term by term or changing the signs. Remember that when we subtract, we sometimes distribute that idea, that subtraction idea. So cosine alpha cosine beta minus cosine alpha cosine beta, well, that's 0. But check this out. Sine alpha sine beta minus a negative. You think about that as a negative, that's sine alpha sine beta minus a negative or plus sine alpha sine beta. So if we subtract this system, we get something very similar to happen that we had right here. We're just going to get the cosines canceling and leaving 2 sine alpha sine beta. So let's subtract them. On the left hand side, we get cosine alpha minus beta minus cosine alpha plus beta On the right-hand side, remember we're subtracting. These are going to cancel. These are not. That's going to create 2 sine alpha sine beta. And if we follow that idea, let's divide everything by 2. Then we'll have solved for sine alpha sine beta, or a product of sine functions with 2 different angles. And we can see it. We can see sine alpha times sine beta equals 1/2 cosine alpha minus beta minus cosine alpha plus beta. These are the first 2 of our product into sum formulas. Notice what they do. They take a cosine times a cosine with different angles and change it into a sum. They take a sine times a sine function of 2 different angles and change that into a difference, or a sum with a negative. So these are our first 2. Now, what's the only one that's missing? Well, we got cosine cosine, we've got sine sine. What we don't have is a sine cosine or a cosine sine. Now, because multiplication is commutative, we don't really have to find a sine cosine and a cosine sine. It's enough just to find a sine cosine or a cosine sine. What that means is we don't have to do this whole add and subtract thing. But let's take a look at this. If we have sine alpha plus beta equals all that sum and difference formula for sine, we have sine alpha cosine beta plus cosine alpha sine beta. Then sine alpha minus beta equals something very similar with a different sign. Let's suppose that we just add those together. If we add them, we're going to get sine alpha plus beta plus sine alpha minus beta on the left-hand side. On the right-hand side, hopefully you see what cancels out. We're going to get 2 sine alpha cosine beta. That's what we're looking for. We're looking for not cosine cosine, not sine sine, but sine cosine of 2 different angles. This is going to give us the last of our product into sum formulas that we actually need. So we're going to cancel these guys and have 2 sine alpha cosine beta. And likewise, if we multiply everything by 1/2 or divide everything by 2, we can solve for the last of our products that we didn't know, sine alpha cosine beta. And that's it. That's the last of our product into sum formulas for sine and cosine. We can see that we can have one of 3 things. We have cosines multiplied with different angles. We have sines multiplied with different angles. We have sine and cosine multiplied with different angles. I said something earlier that maybe now you can see. We don't need both sine times cosine and cosine times sine, because whatever these angles are doesn't really matter for the formula. If you have sine alpha and cosine beta, or cosine alpha sine beta, those variables don't really determine what your angle is. Your angle determines your angle. It doesn't really matter what those are. So we only need one formula there, and that's our last one. So what we're going to do is I'm going to come back, show you how to use these with just 4 examples to illustrate that, and then we'll talk about our last 4 formulas, like ever, for trigonometry before we get into some of our triangle, right triangle trigonometry, law of cosines, law of sines. So hope you're ready for it. We'll come back with a couple more examples. So let's look at how to actually use these. Oftentimes we're given some junk, some trigonometric junk, and asked, find an exact answer for this. Well, that's pretty hard to do with angles that are not on a unit circle, like 285 degrees or 75 degrees. I know we've been dealing with radians very often, but it's time to start thinking about degrees, because as we move toward right triangle trigonometry, sometimes we deal with those quite a bit more. So I'm going to start prepping you for that as well. So let's suppose that we had these angles that are clearly not on the unit circle, but you still want an exact answer for them. That's pretty difficult. So one thing that we can do, like I've shown you with a lot of other formulas, is if we have a product, sine sine, cosine cosine, or sine cosine, we can change it. As long as they're multiplied together, we can change those angles. Hopefully, it creates something a little bit easier to deal with on the unit circle. So let's take a look at this. This is sine of an angle times sine of a different angle. The reason why I say sine of a different angle is because if they're the same angle, you can just get sine squared of that angle. We have some other identities that deal with angles that are the same, like we dealt with double angle formulas, things like that. But here we have two different angles and a product of two sine functions. So let's take a look at what our formula says. We just created it, but our formula says if you have sine of one angle times sine of another angle, we're going to have cosine of subtract the angles minus cosine of add the angles. And that's really how I think about it. We put a 1/2 in front of it, and this will simplify this problem for us and allow us to find some things that otherwise would not be on our unit circle. So let's go ahead and do that. So we know we're at 1/2. All of these product to sum formulas start with 1/2. The sine times sine says take your cosine, subtract your angles, minus cosine of add your angles. I typically write these out every time just so that I can double check my work, make sure I'm not accidentally subtracting or adding something wrong in my head. I'm always just double checking. So I know I have sine, got it. 1/2, got it. Cosine, I've subtracted, it looks good. Minus sign is really important. Cosine of, okay, now I've added them. Then I'm going to go ahead and simplify and hope that this is something I can work with a little bit nicer. So 285 minus 75 is 210. $285 plus 75 is 360. Now that's really nice because 360 degrees is one full revolution, just like 2 pi. So I already know that one, that's on our unit circle. 210 degrees is also on our unit circle. So we might want to have our unit circle handy because we don't deal with degrees all that much, or at least we haven't so far. So let's take a look at this. Cosine 360 degrees is great. That's the same exact thing as 2 pi. So cosine of 2 pi, that's 1. So I already know that one. That's fantastic. This is going to be 1. But 210 degrees is also on our unit circle. Right there. It's the same thing as 7 pi over 6. So cosine of 210 degrees, or 7 pi over 6, is negative square root 3 over 2. So we still have our 1/2. We looked up cosine 210 degrees. We looked up cosine 360 if we had to. That's pretty much it. I mean, we can do a couple things to simplify this, like maybe factor out a negative would look a little bit better. You could find a common denominator to make one fraction, but ultimately what we would get is exactly this. This is your exact answer. I'm going to factor the negative. Make sure you factor from both terms and leave it just like that. Let's take a look at another one. We look at cosine 285 degrees times cosine 195 degrees. Remember, we have a formula that will deal with any of these products of sines and cosines. We've dealt with sine times sine. Now we see cosine times cosine. So let's take a look at the formula. Cosine times cosine of two different angles is put your 1/2, like all of them have. Then we're going to have cosine of subtract the angles plus cosine of add the angles. Exactly the same thing that we did, just we're adding here instead of subtracting. So let's copy that. We're going to start with our 1/2. Cosine of subtract them. Plus cosine of add the two angles. That follows exactly what we know that formula is going to do for us. It says that we're going to take, subtract the angles, add the angles, cosine in both places, and add them together. So we've done exactly that. So if I take 285 degrees and subtract 195, we're going to get exactly 90 degrees. So this is cosine of 90 degrees. That's pretty convenient because that's the same thing as pi over 2. When we add them together, we're going to get cosine of 480 degrees. Now that's great. Cosine of 90 degrees is on our unit circle. Cosine 480 degrees, not so much. Remember, even though we're dealing with degrees, you can still subtract a period from any of these angles. If we had like cosine of 5 pi over 2, we would subtract 2 pi. If we have cosine of 480 degrees, let's subtract 2 pi, but do it in terms of the type of angle that you're measuring in. So if our period is 2 pi or 360 degrees for cosine and for sine, and 180 degrees or pi for tangent, we can always subtract that or add that and get the same exact value on our unit circle. So if we have 480 degrees here, that's not on there. Well, subtract the period. If we subtract 360 degrees, we're going to get 120 degrees. Again, cosine 90 is pretty nice. That's pi over 2. That's going to give us 0. So cosine of 90 degrees is 0. Remember, we're looking at the x-coordinate for cosine. Cosine of 120 degrees is same thing as cosine of 2 pi over 3. Those are the same angle. It's going to be negative 1/2. So 0 plus negative 1/2 times 1/2, that's negative 1/2. That's 1/2. So 1/2 times negative 1/2 is negative 1/4. Now we've done something pretty impressive. We found an exact value, not an approximation. You can do that with the calculator really easily. But we found an exact value for a product of two functions of two angles that are not even on our unit circle. And that's what a lot of these formulas let you do. They let you work with things that otherwise you might not be able to do. So let's go ahead and we'll come back and do one more with a sine and a cosine. So we've dealt with sine, cosine. We'll do a sine, cosine. Let's keep on going. So a lot of times we're asked, can you express this product in terms of just a sum of sines or cosines? It helps a lot in calculus to write things as sums rather than products because you have a different rule for them. And it's a little bit easier if things are just added rather than multiplied. And you're going to get there. But just know that sometimes we want to break up products into sums. So let's suppose we wanted to do that. So we have sine of 4 theta times cosine of 6 theta. We get a sine and a cosine multiplied together as a product. Here's what this formula tells us to do. It says put your 1/2 like all of them have. We have sine of add the angles plus sine of subtract the angles. This is the only one we need for sine and cosine. So let's go ahead and try that. Sine 4 theta times cosine 6 theta. Let's start by putting our 1/2. Sine of add the angles together. Plus sine of subtract the angles. Now you're going to know something very important. While it's not imperative which angle you call which, it is imperative that you add them, or, well, namely subtract them in the proper order. So you cannot do something like 4 theta plus 6 theta and then 6 theta minus 4 theta. That doesn't work. And the reason why it doesn't work is because this does have an order for it, for the angles. You'll get a negative angle in there. Now, that's fine. We can deal with it, but you have to know that sign. You see, sine's an odd function. If we want to change the sign of the angle, well, then we need an identity to do that. And because sine's odd, we can. It's just that we have to know the proper sign in order to get it correct. So we got this. We said, hey, sine, cosine, we have a formula for it. We're going to double check. Looks like we've got it right. Sine of added them plus sine of subtracted them. Now I'm going to simplify a little bit. So I'm thinking, hey, sine of 4 theta plus 6 theta is 10 theta. plus sine of negative 2 theta. Now, I'm really hoping that you remember that because sine is an odd function, you can change the sign of your angle provided that you change the sign of your function. Odd means opposite inputs give you opposite outputs. So if I change that sign, I have to change the whole sign. I'm not just pulling out the negative. If I could do that, why wouldn't I just pull out the 2 and pull out the 10 or pull out the 4 and the 6 and call it good? We can't. We need identities to change angles in trig functions. Always. So if I want to change that to a positive, I need to change the sign of my function. Now, could you just take and subtract those and make that sine of 8 theta? No. That's the reason a lot of identities exist, is to let you do things like that, but you got to follow the rules. If we just subtract them, we're making up our own identities, and that's not okay. That's not a good thing. A lot of people run into a lot of problems doing that. So this is as good as we can get. We cannot simplify any more and make it look any better. This is in terms of all signs. They're being subtracted. And so this would be somewhat easier to deal with if we had to do certain things later on in math that you're going to find out. Okay, one last one. How about cosine 3 theta times cosine 4 theta? We see a cosine times a cosine again. Really, you should stop the video and try this on your own. Just pause it. See if you can identify the proper formula to use. See if you can evaluate it appropriately and simplify it. If we run into evenness versus oddness, remember cosine is an even function. Let's give it a try right now. So we've got 1/2. They all start with 1/2. Cosine times cosine of two different angles is this formula right there. We're going to take cosine of subtract plus cosine of add the angles. And so we've done that. Cosine of subtract the angles plus cosine of add the angles. We're going to double check. It looks really good. We have to subtract the angles in order. That's really, really important. And we've done that. First angle, second angle, I've subtracted them. Now, let's go ahead and simplify this. 3 theta minus 4 theta is negative theta. At the same time, 3 theta plus 4 theta is 7 theta. Now, there's not a whole lot we can do with the 7 theta. We don't even know that angle, but we can use the fact that cosine is even to say opposite inputs give you equal outputs. That's how every function works. So instead of just pulling out the negative, that doesn't work at all, actually. We're thinking, because cosine's even, if I change the sign of my input, or change from negative theta to theta, it will not affect the sign of my output. So I'm going to remove that negative. It's going to look like it just disappears, but we're using the fact, the identity, that cosine is an even function that says opposite inputs equal outputs. That's as simplified as we can get. We've just written this as all cosines in a sum. Sometimes it's a little easier to deal with. Now, I said something earlier. I said that the order really, really matters on what you're doing with these angles. You have to subtract them or add them in the same order, mostly subtract them. But I also said that multiplication is commutative, so you should be able to switch these around and get the same result. You can, as long as when you switch them, you maintain the order. You can probably see it here, but cosine of 3 theta minus 4 theta, if I reverse this, would change to cosine of 4 theta minus 3 theta. Well, that's different. It is, but because cosine is even, it will maintain that sign. That's absolutely fine. One thing that we can't do, remember that sine and cosine, while you could commute them, if you have cosine 6 theta, sine 4 theta, that would no longer fit that formula. This says sine has to come first. So if you're ever given cosine, sine, commute them first. Then use the formula and it'll work out just fine. As long as you're maintaining the order when you subtract, it's going to be just fine for you. So let's go ahead and come back. I'm going to give you 4 new formulas, show you how to use them, and do one more example of how to solve an equation. Okay, so as you can see, I've put up 4 new formulas for you. I'm going to lead you through 3 examples. To use 3 of these, They're very, very similar in what you do. As far as our product and the sums, we're now just going from sums into products. And so they're used quite similarly. All of the ones that you'll encounter with this are fairly similar to what I'm giving you. So let's go ahead and see what's going on here. If we want to add two sine functions with different angles or subtract them, or add two cosine functions with different angles or subtract them, we now have a formula to do that, to put them into a product. Now, does it help? Yeah, yes, we go both ways, from products into sums, from sums into products at different times in math. And we have a product to do that. We have a way to do that, I should say. So sine of alpha plus sine of beta is 2 sine, you add the angles over 2, cosine of, you subtract the angles over 2. If we want to subtract our sines, we have something very, very similar. Be careful on your signs here. If we want to subtract our sine function with different angles, we have 2 sine, you subtract the angles over 2, cosine, you add the angles over 2. Cosine's a little bit different. So cosine of alpha plus cosine beta, so two different angles, adding the cosines, we have 2 cosine, add them over 2, cosine, subtract them over 2. If we want to subtract the cosine functions, negative 2 sine, add them over 2, sine, subtract them over 2. So we're just switching our functions here from cosines to sines and putting a negative in front. Let's see if we can do this with a few examples. How about cosine of 2 theta plus cosine of 4 theta? So we're going to check out our formulas. We know that we have a sum of cosine of 2 different angles. So that's going to be right here. So what's it say to do? Put the 2 first, cosine of add them over 2, cosine of subtract them over 2. 2 cosine of add them over 2. Cosine of subtract them over 2. Remember, just like in the product of sum, the order is very important here. So we want to make sure we're adding and subtracting, especially subtracting, in the proper order. And then we're going to simplify. So 2 theta plus 4 theta, that's 6 theta. Over 2. And cosine of 2 theta minus 4 theta, that's negative 2 theta over 2. Take some time to simplify the fractions. We're going to get 3 theta and negative theta. Now, the cosine 3 theta is set. You can't do anything with that. But cosine of negative theta, because cosine's even, we know opposite inputs give us equal outputs. We can change the sign of our argument without changing the sign of our function. That's it. Flip the sign, you're good to go with even functions. So 2 cosine 3 theta and then cosine positive theta. It's really tempting to want to pull the 3 out. It's really tempting to combine your cosines and combine your angles. You can't. Unless you're using an identity, the stuff we want to do by pulling stuff out, it really does not work. So leave it just like that. You're done. It's kind of nice, kind of refreshing that you don't have to do anything more with that. You really can't unless you have an identity. Let's take a look at this. We have cosine functions being subtracted with different angles. If we have them subtracted, they count as a sum into a product formula, but we're just subtracting instead of adding. And that's okay. It's like you're adding the negative. So we're right down here. We're subtracting cosines with different angles. We're going to start with this with a negative 2. Then sine, add them over 2. Sine, subtract them over 2. Negative 2, sine, let's add them. All over 2, so negative 2 sine, add your angles, got it, over 2. And then sine, subtract your angles over 2. We have a bit of simplification to do here. One thing you could do, you could multiply both your numerator and denominator all by 2 and distribute and kill off your fraction right now. If you want to do that, that's totally fine. So we get 2's cancel theta, 2's cancel 3 theta, 2 times 2 gives us 4. You can do that. If you prefer to make a, if you already have a common denominator, make this one fraction, you can do that as well. I'll show you that here. It just might start looking a little awkward with complex fractions. So theta over 2 minus 3 theta over 2 is negative 2 theta over 2. Now our 2's are going to simplify, giving us negative theta over 2. And 4 theta over 4, we can simplify that. Now, please keep something in mind. I said something that's kind of confusing for some students to understand. What I told you is you cannot manipulate the argument to change it, but then we're adding and subtracting things in here, and that seems maybe contradictory. Keep in mind, I'm not actually changing the argument, I'm simplifying it. I'm not moving anything out. I'm not putting anything in. I'm not changing the sign. I'm just manipulating this inside, but I'm leaving it inside. I'm not pulling it out. I'm not changing that from what it is. I'm just making it look a little different by simplifying the fractions in there and things. I'm not changing the value of it. To change the value of it, the sign of it, you need an identity. I hope that makes sense to you. We're just kind of messing with this to make it look prettier. We're not fundamentally changing it, like changing that sign to a positive. That's different. Fundamentally changing, like pulling a 3 out or something, that would be changing the value. We're just changing the look by simplifying our fractions. So 4 theta over 4, we are just going to get theta. Now the negative theta over 2, that's inside sine. So if we wanted to change that sign of the angle, we could, but we need an identity. Because sine is an odd function, opposite inputs give us opposite outputs. If we change the sign of our input, it'll change the sign of our function, our output. So we're going to do that. We're going to change this to a positive, but it's going to change this function to a negative. Negative times a negative is going to give us a positive. So I'm going to change this, but it's going to change my sign here. So I'm showing that right now. I'm showing that this is odd, so I can do this with it. Now a negative times a negative is going to give us a positive. That's about as good as we can get, as simple as we can make that. No, this 2 and that 1/2 do not cancel because, again, to change your argument fundamentally, to move things out, put things in, you need identities. Okay, last one. You should really pause it and try this on your own. Take a look at which of these formulas actually works. See if you can understand the concept of what's going on behind it, and then simplify as much as you can. So for us, we have sine of theta over 2 minus sine of 3 theta over 2. So we have two sine functions with different angles being subtracted. It looks like that one. So what's it say? Put a 2. Got it. Sine of subtract over 2, cosine of add over 2. So we have two different functions there, sines and cosines. So we've got 2 sines subtract the angles over 2, cosine add the angles over 2. You can see the only one we're not using in these examples is that one. It's very, very similar to everything else we've done, so follow the same pattern. But we always do want to double check. So I want to double check subtract, got it, angles look really good. First minus second, so I have an order over 2, okay. I'm adding them over 2, I haven't messed up any of my angles. Now we're going to go ahead and simplify. I showed you that you can multiply by LCDs, that's nice. These already have a common denominator. If you just want to combine them, that's totally fine too. I'm going to do that here. So theta over 2 minus 3 theta over 2 is negative 2 theta over 2. So negative 2 theta over 2 all over 2 still. And then we'll have 4 theta over 2 all over 2. And fortunately, we can simplify that. Negative 2 theta over 2 is negative theta over 2. cosine of, well, let's see, 4 theta over 2 is 2 theta over 2. Divided by 2 is just theta. Now I'm hoping you see what's going to happen next. Cosine looks great. Cosine theta, you're done. Sine of negative theta over 2. Think about what sine is. Is sine an even function or an odd function? We're thinking that's an odd function. What do odd functions do? Opposite inputs give us opposite outputs. So if I'm going to change the sign of the input, it's going to change the sign of my output. If I want to change this, in other words, it's got to change that sign. Evens don't do that. Opposite inputs equal outputs. So if I want to change the sign of my input, I don't change the sign of my output. That's why for cosine with a negative, it looks like you just drop the negative. It's because it's an even function. The sign of the function does not change when you take an opposite input. So I'm going to make this negative. This says change your input for an odd function. You have to change the output sign. That's as good as we can get. That's as simple as we can get. That's taken a difference of sine functions with two different angles and made them a product and only sines and cosines. Sometimes it's very valuable. I hope that's made sense. We're going to come back and do one equation, and then we'll call it good. So you might be wondering, why in the world do we do a lot of this stuff? Why do we change from a sum to a product? Why do we change from a product to a sum? A sum to a product is very nice. Why? Well, because if you're trying to solve equations, a sum cannot be solved very easily by stuff that's nice to use, like the zero product property. But products can. Think factoring. Like factoring works because you create these factors that you can set each one equal to 0 by the zero product property. What could you do there? Like we can't pull out a 2, we can't pull out a 4, we can't factor anything about this. In order to change the arguments, you need identities. If they're not the same, you can't add them. You can't factor them. You cannot factor a sine out here. You can't factor a 2 out here. You can't do anything with it. You can't set each of these equal to 0. They're not products. They're a sum. And so a lot of times when we deal with equations like this with different angles of sine functions or cosine functions added or subtracted, it's very nice to make them a product. We have the same situation that we have here. Notice that. The sines are being added with different angles. Let's use our formula. So this says you're going to take sine of add over 2, cosine of subtract over 2. So we are solving an equation. I'm working on this side. I still have this equal to 0. I'm not putting things in random places or anything. I've used the formula appropriately. Let's see. I had sine of different angles being added. I've got 2. I got 2. Sine added over 2, cosine subtracted over 2 in the proper order. First angle, second angle. So I want to make sure that's correct. And now I'm going to simplify it. So I did this one pretty quick, but 2 theta plus 4 theta is 6 theta. 6 theta over 2 is 3 theta. 2 theta minus 4 theta is negative 2 theta. That negative is important. Divided by 2. That's going to give us negative theta. So let's write that. Now, what do you see? Hopefully you see that cosine of negative theta is an even function. I'm going to change the argument without changing the function's sign. Change the sign of the input. It will not change the sign of output for even functions. Now, this is why we might want to use a formula like this to change from a sum into a product. You see, if we have this now as a product equal to 0, the zero product property still works. Let's take all of our factors that contain variables, not the 2. The 2 doesn't even matter here. But if we take all of our factors that contain variables, we're able to set them equal to 0. So if things multiply together equals 0, each one of those things, those factors equal to 0, provides a solution for us. So I'm going to take sine of 3 theta equals 0. and cosine of theta equals 0. Let's start with the cosine theta equals 0. So we pull our unit circle out, we take a look at it and go, hey, when does cosine theta equal 0? When do we have an x coordinate of 0? Remember, cosine of theta says our x coordinate for this angle is, in this case, 0. That would happen at pi over 2 and at 3 pi over 2. That's when our x coordinate is 0. We're done with that. We're done with this one. This one's a little trickier. Man, I hope that you remember that when we have like sine of 3 theta, one of the first things that we learned about solving these equations was you can do a substitution. It puts more frequency on the same period. Remember, that cuts your period by 3, or it compresses it into a third of a normal period. So 3 of them are going to fit on a normal period. That compresses it so that more fit between 0 and 2 pi. And if we're looking for solutions on 0 to 2 pi, which we almost always are, then we have to take that into account. So here's what to do. This is a recap. We would call whatever that angle is something different. Let's call it alpha for a second. So alpha equals 3 theta. We're making a substitution. Can you solve that now? Yeah, that's not bad. Sine of alpha equals 0. Alpha is, let's see, if sine of alpha gives us the y coordinate for this particular angle and says your y coordinate is 0, I'm looking for angles that create a y coordinate of 0. Sine is the y coordinate on a unit circle. That's going to be 0 and pi. Now, we just talked about this, but because that shortens your period or compresses it, more will fit on the same period. In fact, whatever that number is, do you remember this? Whatever that number is, add periods. So 2 pi for sine, pi for tangent, 2 pi for cosine. Add periods until you hit that many cycles. So I'm going to add 2 pi. I'm going to add 2 pi again. So 0 plus 2 pi is 2 pi. Add another period, that's 4 pi. How about for 4 pi? Do the same thing. Remember that 3 of these periods are now going to fit in the original 0 to 2 pi. So I'm going to add 2 pi again. That's going to give us 3 pi. Add it again, you're going to get 5 pi. So we have 0 pi, 2 pi, 3 pi, 4 pi, 5 pi. Those are all the solutions, way more than 2 pi right now for alpha. But look what's going to happen. Because we used a substitution, because we said, hey, we're calling 3 theta into this alpha. Alpha can be this to satisfy a y coordinate of 0. Either 0 or 2 pi or 4 pi. Or we could do sine of pi, or 3 pi, another revolution, or 5 pi. When we take and put our substitution back and say, yes, but do you remember, alpha is really 3 theta. What's going to happen? We have to divide everything by 3 in order to solve for theta. That brings it from way outside of 2 pi, like 5 pi is way outside that, brings it from way outside 2 pi back into it because it's compressing that. It's making more periods fit on the original 0 to 2 pi. So let's divide everything by 3. So we would get 0, pi over 3, 2 pi over 3. 3 pi over 3 is pi. 4 pi over 3 and 5 pi over 3. Notice what happened. All of these are between 0 and 2 pi. 1 revolution on the unit circle. We just happen to fit more periods on that original revolution. So combining these solutions with this solution satisfies that equation. I hope that makes sense to you. I hope that you're seeing the utility in using this sum to a product, so that way we can make them factors, use the zero product property, and solve them with a substitution like we already know. Otherwise, if you don't see that, that gets really, really hard. I'm not obviously doing more, because the only things I can really do are put a minus there, or do cosine plus cosine, or cosine minus cosine, and we deal with the same type of formula. We do the same type of problem. So you can do that on your own. Hopefully you understand what we've been talking about. Hopefully that this helps you. I hope you're enjoying the videos. Have a great day.